All right, welcome back. All right, now we're going to start picking apart a list of forces that are at work in the atmosphere. Because what we're going to do is we're going to make an inventory of those forces that are going to be able to do things like act on an air parcel in the atmosphere. And then we're going to be able to think about ways in which they might be in balance or in ways in which they might not be in balance, creating winds that are or are not in any kind of force balance and so on. Now what I'm going to do here is along the left side of the screen here, I'm going to be making an inventory of the forces that are at work. It turns out there's going to be 5 of these forces, and it's just going to be useful to have a list of them off here on the side of the screen. And the first force that we're going to work on here is the so-called pressure gradient force. The pressure gradient force. To understand the pressure gradient force, you need to understand this word gradient. A gradient, boy, gradient is a word we're going to see so many times over the course of this semester. A gradient is how some quantity changes over a distance. Not over a time or whatever, or over a distance. So, we're going to need to have some kind of observations of something. In this case, because it's the pressure gradient force, it's clearly going to be about the gradient of pressure, how pressure changes over a distance. But to understand the idea of gradient, let's talk about gradient in a way that you've probably heard about it in your day-to-day life, and that is to do with like slope of terrain. Now this little blobby thing that I have here on the screen here, that is a map. It happens to be a map of an island. Honestly, I'm not sure. It might be Hawaii. I don't remember. But this is a contour map of heights of Hawaii. There's some mountains and so on. You can see those contour lines that show like 1,000 feet, 2,000 feet, etc., showing the contour map of this island. Okay? We could, at any given point to our little pointer to a spot here and read off of this map what the height above sea level is. Well, if you ride bicycles, if you do mountain biking, if you do any kind of hiking, you're familiar with the idea of a gradient, sometimes it's said as grade, and how that's going to, these maps can be used to tell you that. I mean, for example, I kind of blew the map up here a little bit in the background here. Look at this blue location right here. At this blue location, if we walked in the direction of this blue arrow, we would be crossing some of the contours of height on the island here. We would walk a while and come across the 1,000-foot contour, and then we walk a little while farther and we get to the 2,000-foot contour and so on. We are walking uphill when we walk in the direction of that blue arrow, but the contours are fairly far apart. We walk a while before we hit 1,000 feet, and then we walk again pretty far before we get to 2,000 feet and so on. Just like the little blue inset picture here. For the hiker on that blue path, this hike isn't really all that steep. It takes a pretty long ways to have a change of just 1,000 feet in the altitude. The contours were far apart. It takes a long time to walk from one to the next. Alright? In contrast, take a look at that red arrow there. For a hiker following that red path, look how close together those contours are. For a little hiker right there following the red direction, he would cross, I don't know, what are we looking at there? It looks like about the 5,000-foot contour, and then he'd walk a little farther and he's already to the 6,000-foot contour. He's going uphill pretty steep. And then just walk a little while farther and he's at the 7,000-foot contour. He's going up a very steep trail, something like what I have there in that red inset. And the way you can tell that it is steep, that there is a steep gradient to that hike, is that the contour lines are close together. The spacing of the contour lines tells us about the gradient. When the contours are far apart, you have over a distance, the quantity, in this case the height of the island, doesn't change all that much. On the other hand, if the contour lines are close together, then over the same distance, that quantity, in this case altitude above sea level, changed a lot, and it's a very steep climb. Well, in meteorology, we don't all that often look at like maps like this of terrain. We would be looking at other kinds of maps, like maps of pressure. Here's a map of pressure that I found someplace, and there's an area of low pressure there in southern Illinois. And based on the weather observations around it, we have drawn these contour lines. Looks like the pressure is about 992 millibars in southern Illinois. And then these contour lines are drawn, these isobars, lines of constant pressure, are drawn about every 1 millibar. So there's a 992 millibar contour line, 993, 994, 95, all the way out to, I don't know, about 1010 near the edges of the map, something like that. You can look at it more closely. Well, if you look at each of these locations on the map here, you can see that, for example, look at the blue arrow there. At the location of the blue arrow, if you walked in the direction of the blue arrow, you would be getting towards lower pressure. But look, you got to go pretty far from like northern Indiana to like north central Indiana before you even move 1 millibar. Okay? Realistically, the pressure is not changing that fast over distance. As you go from one location to another, there's not that big of a change in pressure. In contrast, look at what's going on there in Missouri here, where I have that red arrow in there. Look how over just a tiny distance you cross a lot of isobars. Okay? There's a very large pressure gradient right there. Over the same distance of, I don't know, maybe 100 kilometers or however long that red arrow is, you cross lots of isobars. And you go from a relatively high pressure, I don't know what we got there, about 1,000 millibars, to a very low pressure of like 992 millibars. Here it helps if we zoom in a little bit there. I don't have all the labels in there. But see how the isobars are very close together on this map, and you cross a lot of them in a small distance. Okay? That is a pressure gradient. And pressure gradients create a force, creatively called the pressure gradient force in the atmosphere. I forgot here, so here's the same map here on slide 20. You zoom in and you can see how the pressure gradient force, the vector here shows that we're not crossing all that many contours here in northern Indiana. Okay. So this pressure gradient force is a force that's being created by the fact that there is a pressure gradient. It is pushing an air parcel. And it always pushes the air parcel in the same direction. It always pushes from higher pressure towards lower pressure. That shouldn't be a huge surprise. In your day-to-day life, you know air tends to flow from places where there's a higher pressure towards air where there's lower pressure. Now, I'm telling you that it isn't, like for example, where would you know that? How about the tires on your bike? The pressure inside your tire on your bike is greater than the pressure outside the tire of the bike. Okay, you've got however many pounds of pressure on the tires. That means that the pressure on the inside is greater than the pressure on the outside. If you open up the valve stem on your tire, air flows from inside the tire towards outside the tire. You would be very surprised if the air went the other way, right? From the lower pressure on the outside of the tire towards the inside of the tire. That would be weird. The Mir space station. The Russians used to have a leaky old space station up in orbit before the International Space Station was built, and it was notorious for losing air. Okay? Outside of the space station, the pressure was low, basically zero. It's space. And inside of the space station, they kept the pressure as high as they could, maybe 1,000 millibars, maybe not quite that, but it was notoriously leaky. Air flowed from there was a pressure gradient force pushing air from the inside of the Mir space station out through the leaks into the lower pressure of the cold dead vacuum of space. A can of hairspray, high pressure on the inside, lower pressure on the outside. You open up the valve by pressing down, air goes from the inside of the hairspray can to the outside. Doesn't matter what kind of example you're using, you know that air wants to flow from higher pressure to lower pressure. Now I'm going to tell you that that's all, in your experience, different than what the wind is going to be doing. I'm not going to tell you that wind is going to go from high pressure to lower pressure, but there is certainly a force pushing it that way. Okay? But there'll be other forces. In contrast, like when you open up the valve on your bicycle tire, air does flow from inside the tire to the outside because there aren't other forces acting on the air at that time. Okay? But in the atmosphere, it's going to turn out there are other forces at work. Here's just another example here. These colors on this map, it's just a color-filled map of pressure, where there's a big area, in this case, of high pressure centered over Minnesota and Wisconsin. And I want you to see that I've drawn on there some vectors of the pressure gradient force. The pressure gradient force vectors all start, we always think about them in terms of where they start, okay? And each of them, wherever they start, the pressure gradient force is always pushing in a very specific direction. It is pushing from high pressure towards lower pressure. And it has to be, notice how they're all pointing away from the H. And they have to be pointing in such a way that they're perpendicular to the isobars. Okay, you don't want to be the pressure gradient force should not be drawn as if it's like crossing the isobars at some angle. They should be perpendicular. Now that's kind of hard to do in PowerPoint, to be honest. It gets a little messy. But you want to see the pressure gradient force vectors crossing the isobars perpendicularly from high pressure to low pressure. And we indicate the strength of a vector by drawing it longer or shorter, where a longer vector represents a stronger force and a shorter vector represents a weaker force. So like for example, across North Dakota there, where the isobars are relatively close together, I drew the force as being pretty strong. The pressure gradient force is pushing pretty hard on air parcels to go that way, across from like Minnesota towards Montana or whatever. In contrast, like over Oklahoma here, I drew a real short little pressure gradient force vector. The isobars are fairly far apart over there. So we still have a pressure gradient force vector that is going perpendicular to the contours from high pressure towards low pressure, but it just isn't as strong. All right. You'll be drawing vectors and so on in your homework and in the lab activities and so on. Okay. All right. The pressure gradient force vectors have to be perpendicular to isobars. They have to be going from higher pressure to lower pressure, and we draw them longer the stronger the force is. Okay, I see all that. Man, the pressure gradient force is really interesting. It has a mathematical representation. It takes a bunch of horrible things that you don't want to think about, though. Partial differentials and so on to write it correctly out mathematically. I think your book actually tries to do so in like a box along the side of the page or something. Don't worry about that. The mathematical way to produce this is fascinating if you're an atmospheric science major, but is not where we're going in the class. I want you to be able to think through which way the force is, not actually compute it on your calculator or something like that. Another interesting thing about the pressure gradient force, the pressure gradient force is the only force in the atmosphere that can take an air parcel that is not moving and make it start moving. There's going to be other forces at work that can slow it down or turn the air parcel, like deflect its motion, but no other force can start an air parcel from a standstill. All right. All right. When you think about pressure gradients and about how the pressure changes from one place to another, in meteorology we almost always are talking about that in the context of like a map, where we're looking at the distribution of the pressures on a horizontal level, like at the surface, and we say, oh look, the pressure is higher here, the pressure is lower there. But there's another way in which pressure changes, and that's vertically. There's a very strong vertical pressure gradient in the atmosphere. The pressure here at the surface of the Earth is in the ballpark of 1,000 millibars, but just as you go up in the atmosphere, the pressure decreases. So, you know, like for example, a few kilometers up in the atmosphere, you're already up to 500 millibars. Wow. So, you know, at the surface of the Earth, I might have to go a few hundred kilometers to have a change of pressure of 1 millibar. But 1 millibar lower pressure is only a few meters above me. Okay? I can go a few kilometers up and be all the way to 500 millibars above ground. Oh. Does that mean that we have a vertical pressure gradient force? Absolutely. In fact, it's huge. The vertical pressure gradient force is describing the way in which pressure decreases with respect to height, and therefore, I'm holding an air parcel right here. I got a volume of air in my hand. Is there a force acting on this air parcel pulling it towards the higher pressure above me? I'm sorry, the lower pressure above me? Yes, it is. It's actually a really, really strong force. Well, then why doesn't the air parcel accelerate upward? Oh, because there's an equal but opposite force pushing the other direction. That's gravity. The force of gravity pulling the air parcel down is exactly the opposite of the force of the pressure gradient force pushing upward. This is a very interesting phenomenon in the Earth's atmosphere, any atmosphere of any planet or moon or anything like that, called hydrostatic balance. Hydrostatic balance. Here the word hydro does not refer to water, it means fluid. And the air is a fluid, it flows. And static as in ain't moving. So hydrostatic meaning as in like, why is it not moving? The hydrostatic balance is the very perfect balance between the vertical pressure gradient force pushing up and force of gravity pulling down. At any given time, at any given volume of air you want to pick in the atmosphere is in hydrostatic balance. It has to be. Now, does that mean that air parcels in the atmosphere can't go up or down? because they're in hydrostatic balance? No. It just means that if there is a reason why they go up or down, it isn't because, like, oh, these air parcels are sinking because gravity is stronger here. Or these air parcels are rising because, like, the gravity is weaker here, or something like that. Rising motions and sinking motions will have to be due to something other than the vertical pressure gradient force and gravity. Okay? It's just that there are other forces that and processes that can cause vertical motion. I'd like to bring this up at this time, though, because this is the first time we're going to see a force balance, in terms of a wind anyway, or in terms of the atmosphere. We're seeing how the vertical pressure gradient force is exactly being balanced by gravity. Then we hit the horrible one, the Coriolis Force. The Coriolis Force. Any fans of The Simpsons out there? You might remember that there's an episode of The Simpsons where Lisa explains to Bart about the way the toilet is spinning. And she explains that the toilet spins the way it does because of the Coriolis Force on Earth. And the Coriolis Force is one way in the northern hemisphere, and the Coriolis Force is the other way in the southern hemisphere. And she explains that toilets in Australia spin the other way because of the Coriolis Force. And I have some news for you. It's comedy gold. But don't get your science information from The Simpsons, okay? She is right about parts of that explanation, but she also is very wrong about, like, why the Coriolis Force is and so on. Coriolis Force is not why your toilet flushes the way it does or anything like that, as you may have seen on The Simpsons or other things on TV or on the internet. Let's spend a few minutes talking about what the Coriolis Force is and what it does. Coriolis Force, what is this? Coriolis Force is named after an old dead white guy of science. His first name escapes me. Is it Gustav Coriolis? Something like that. Old French engineer who was the guy who figured this whole story out and so on. And it was like in the 1800s as to figure out what's going on. And he determined that there would always be as long as an object was in motion. He was actually experimenting with cannonballs. But it could have been anything from cars on the road to air parcels in motion to missiles in the air. Any object that is in motion is going to be deflected by what came to be known as the Coriolis Force, as in it will be turned. It will be turned to the right if the object is in the northern hemisphere. It will be turned to the left if it is in the southern hemisphere. I try to draw this over here a little bit here. Here I have two objects that are in motion, these little balls or whatever, maybe they're air parcels or something like that, and v is their velocity, that's the direction they're moving. We would draw their Coriolis Force as being 90 degrees to the right of the direction that they're moving, because in the northern hemisphere the deflection is to the right. So that air parcel that's over here, as it is pulled off in this direction, it's going to be deflected to the right. I wonder why. Well, we'll get there. Let me tell you another thing, though, you got to understand about the Coriolis Force first. We know, both from math and from experimentation and so on, that the Coriolis Force is going to be stronger the faster the object is moving. So, again, I drew two objects here, and the velocity vectors are drawn in blue, and one has a very short velocity vector and the other has a very long velocity vector, indicating it's faster, and the short one indicates that it's slower. Okay, in both cases the Coriolis Force vector is drawn 90 degrees to the right of the velocity, but in the case of the faster motion the vector is longer, and in the case of slower motion the vector is shorter. So, if you have a really fast motion, like an ICBM coming in, the Coriolis Force acting on that will be very strong. Or a bullet, the Coriolis Force on it will be very strong. A relatively slow motion, I don't know, a wind, or you walking down the street, or the basketball when you throw it, the Coriolis Force is going to be so weak you probably aren't going to notice it. Why? Why don't we notice it in our daily lives? I mean, here's a launch of a space shuttle here, actually, from there. Time-lapse picture so you can see how it was launched. Why don't we notice the engineers who are launching the shuttle have to know about the Coriolis Force? How come in our day-to-day lives we don't notice it? When my kid misses a pitch at his baseball game, how come it's not the Coriolis Force that made the ball turn that he didn't notice it? Well, the Coriolis Force is important for motions that are very fast, like aircraft and missiles and winds in the jet stream and so on. Or if an object is in motion for a really long time. I mean, the wind, as it blows around a mid-latitude cyclone, we'll learn about those words in just a little bit, it'll be in motion for days as it goes around there. Even though the Coriolis force isn't all that strong, it's going to have plenty of time to act. Okay? Even a weak force added up over a long period of time will produce a big change. But a baseball, which isn't all that fast, and is only in the air from the pitch to the catcher for a fraction of a second, the deflection by the Coriolis force is, a millionth of an inch or something like that. Okay? It isn't moving that fast, and it isn't in motion that long. Alright. Why does the Coriolis force happen? Okay. We have a Coriolis force in our atmosphere for the fact, well, it's a bit complicated. It's because the Earth is round, and it's because the Earth is rotating. Now, I want to show you the basic outline of why this is, as to why this produces a motion, but a force that deflects force motions to the right. And in order to do that, I have a little flash animation that I put together, again, like 10 years ago or something. And rather than play it in, you can go to this link right here if you want to actually play the video animation yourself. Although I'm also going to now embed it into this slide right here as a video here. Alright, so let me go ahead and reload this page that I have back here. I know you can't see it on my screen, you're seeing it on yours. I want you to picture an object that's going around the Earth at some location, at some latitude. Like that ball there is. And as it goes around the Earth, it's moving at some speed. It takes some amount of time to go all the way around the Earth. Okay? But as for any rotating object, as it's revolving around an axis, if it gets closer to that axis, it's going to rotate faster. That's conservation of angular momentum. You may have seen that in a high school science class or something like that, where the teacher, was spinning you on a office chair, and as you pulled in closer to the axis of the chair, you spin faster, and if you put your hands out, you spin more slowly. It's how ice skaters do it. We're going to come across that idea of conservation of angular momentum again later. So if you watch the animation here, you can see how, this object, in this case this little red ball that I drew here, starts off going fairly slowly around the axis of the Earth, but if I pull it in closer to a different latitude line, it starts going faster and faster. Maybe it originally took some number of time, let's say X hours, for it to go all the way around the Earth, but when I brought it in closer to the axis of the Earth, it happens faster. It gets around the Earth in less time. Alright, let me advance to the next part of this here. Hold on. Oh, wrong slide. Wrong mouse, rather. Well, any object just sitting there at the surface of the Earth is going around the axis of the Earth, like that little ball is there right now. It is in motion about the Earth's axis. So if I were to make that object now start heading north, again, watch the animation closely. If I take that object and I start bringing it closer to the north, I'm getting it closer to the axis of the Earth. Imagine if I were standing at the North Pole and I had a really long fishing line, and I had cast south, well, I guess every direction is south at the North Pole, and I caught a fish down here on this map someplace. As I bring the fish in, I'm bringing that fish closer to the axis of the Earth. That fish was originally just sitting there at the surface of the ocean, going around the axis of the Earth once every 24 hours, but as I reel that fish in, he's getting closer to the axis of the Earth, and therefore, by conservation of angular momentum, he goes faster now. He's taking less than 24 hours to go all the way around the axis of the Earth. Now, it can be kind of hard to put those two ideas together, but what that means is as I bring that fish inward, from the fish's point of view, he's going to get turned to the right. His motion is going to be deflected to the right. That's an important point here. When I say these objects are getting deflected to the right, I don't mean to your right or to the right side of the page. I mean right with respect to the motion of the object. When I throw the baseball from the pitcher to the catcher, the ball deflects a little bit to the right of its motion. Okay? Whether that's to your right or that just depends on where you're standing. We mean to the right of the motion. Now, here's the deal. The Coriolis force is really hard to think about. Even people with PhDs in meteorology often can't explain the Coriolis force all that well, and frankly, I'm not sure I did all that well in that example right there either. But here's the deal. Anytime you have a motion on something that's rotating, you're going to get a Coriolis force. It doesn't have to be on the Earth. And I have two examples here of links that you should definitely go try and see. where people are showing examples of rolling or throwing balls on merry-go-rounds. It's actually really cool. I've been trying to figure out how to get a hold of a merry-go-round to make my own videos like this. Now, as the ball is rolled on the merry-go-round, what you're going to see is they're going to try to roll the ball in a straight line, but it gets deflected to the right. Or actually, it gets, I think, deflected to the left in theirs, because I think the merry-go-round is spinning in the opposite way of the Earth. Or you'll see in one of the videos there where they're passing a ball, and you can clearly see in the video how it deflects as they try to throw the ball on a rotating system, in this case on a merry-go-round. It's pretty cool.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis Force, whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
But the key there to understand then is that the Coriolis Force acts on objects that are moving, and it deflects motions to the right in the northern hemisphere. It is true that it also deflects motions to the left in the southern hemisphere, but we're not going to get bogged down on southern hemisphere stuff in this class, just because, I mean, I don't have a lot of students in my class who are from New Zealand or something like that, okay? By the way, it does mean that the Coriolis Force is zero at the equator. That's going to turn out to be important when we start learning about tropical weather phenomena, in particular hurricanes. Man, everybody hates thinking about the Coriolis Force. Let's worry about the Centrifugal Force instead. The Centrifugal Force is that force that kind of pushes you outward when you're on something that's rotating. When you are... Oh man, my kids love to go crazy fast when they're on a merry-go-round. And if they don't hold on, poof, they get thrown off the merry-go-round, right? That's the centrifugal force, which we abbreviate in meteorology CN for complicated reasons. Alright, centrifugal force is going to affect any object that's rotating. And lots of things in the atmosphere rotate. You know, cyclones, hurricanes, tornadoes, dust devils, and so on. Actually, lots of other things are going to have a rotating component to their motions as well. The centrifugal force then will always be acting on something that is rotating, and the way we draw the centrifugal force is like how we have these red vectors on here. Okay, those would be like indicating that the centrifugal force is pushing outward from the axis of rotation. Okay, it always just points outward. It doesn't matter whether you're spinning clockwise or counterclockwise. The centrifugal force pushes outward. Centrifugal force is not so hard to think about, and it's going to be important in some pretty cool phenomena like tornadoes. And finally, friction. Friction is our fifth force here. Now, when we talk about friction in the Earth's atmosphere, we are not talking about, you learned about friction like this in high school science or something like that, right? We're not talking about like rubbing two air parcels together or something like that. Generally speaking, air is pretty close to frictionless in terms of how like air flows past each other and stuff like that. When we're talking about friction in the atmosphere, we're talking about friction between the surface of the Earth and the atmosphere trying to flow over it. I mean, as the air tries to flow over buildings and through trees and cropland and over hills and power lines and billboards, those objects are exerting a drag or a friction that slows those winds down. Okay, so that's what we mean when we talk about friction. So right off the bat, it should be clear, friction is mainly a phenomenon that we worry about in the atmosphere close to the surface. Up high above the atmosphere, once you're more than about a few hundred meters up or something like that, the friction caused by the wind trying to flow through trees or trying to flow through cropland or trying to flow over hills or past billboards or whatever is now basically nothing. So it's really only a phenomenon near the surface, and it is definitely going to be more over land than over ocean. Now, I know at the ocean there's, waves and stuff like that, but realistically over the ocean, the surface is much smoother than it is over, say, forests or something. I mean, think about how, as the wind flows through, say, a forest, it has to flow across, there's all those leaves and all those branches. There's billions and billions of leaves in a forest and tree branches and so on, not to mention any hills that are going on or whatever else, all that exerts a force of friction on the air. Whereas, at the ocean, yes, I mean, right where the air is touching the waves or something, there might be some friction, there will be some friction, but it just doesn't add up to all that much. There's not that much surface interacting with the atmosphere. Friction is greater the faster the motion is. I think you probably would have realized that. If you think about friction in this sense, when you rub your hands just gently together, you're not really producing very much friction, but the faster you rub them together, you can feel the friction increases. So, if we are going to be thinking about how we're going to draw the vector associated with friction on a map or something like that, if we have an air parcel like this one that I have right here, and it's moving in the direction I have labeled V, we're always going to label friction as being exactly in the opposite direction as the velocity vector. Because all friction can really do is slow motion down. Right? Friction doesn't... You know that if you take a book and you set it at the end of the table and you give the book a push, the book is going to start sliding across the table and it's going to slow down and eventually stop due to friction between the book and the table. All the friction can do is slow the book down. You would be very surprised if you gave the book a push and it started going in a circle on the table. Now, if you could somehow make the book go across a table for thousands of kilometers and be in motion for a very long time, the Coriolis Force might eventually cause the book to go into a big circle. In fact, it would. That's called an inertial oscillation, although you don't need to know that term in this class. Might happen in the wind, but it's not going to happen with the book being pushed across the table. So friction just, it's your experience, all it can do is slow things down. You'd be very surprised too if you gave the book a push and it got going faster and faster and went shooting off the edge of the table. You know what friction can do. So what happens here is that we have 5 forces at work in the atmosphere. Pressure gradient force, the gravity, the Coriolis force, the centrifugal force, and friction. Air is not meaningfully affected by other kinds of forces that are at work in the natural world. I mean, air doesn't get affected by magnetism or anything like that. These are the only forces that are meaningfully affecting the wind. 5 forces doesn't sound like such a bad thing, but the truth of the matter is human brains are terrible at that. Human brains are not good at keeping track of 5 things at the same time. While it is true that on this volume of air right now that I got right here in my hand there, I'm holding an air parcel right here. There's 5 forces acting out on it right now. Gravity, friction, Coriolis force, centrifugal force, and pressure gradient force. The truth of the matter is, I am not good at keeping track of 5 forces, and neither are you. It has to do with how human brains work. It is going to be better, if we're going to be understanding what's going to be causing this air parcel to move and form wind, we're going to need to be able to think about situations in which we can narrow this down. Where we can start assuming that some of these forces are so much smaller than the others, we don't need to think about them and we can throw them out. We can ignore them. Because we are not good. It's just not how human brains work. We're not good at thinking about 5 things at the same time. It's going to be best if we can narrow it down to just 2. If we can say, look, 3 of those forces are small, we can ignore them in a tornado. Or in a cyclone, or whatever. We'll get there, okay? That's where we're headed with all of this here. But before we actually try to do that, let's actually answer a couple more questions about what we just learned about all these forces. Question 3. Which force in the atmosphere is the only one that can start an air parcel in motion? Is it the pressure gradient force, the Coriolis force, the centrifugal force, or, hey, wait a minute, no, actually all these forces can do that. Make a choice from those 4 options and get a little feedback before you move on to question 4.